welcome to this first afternoon of DevOps UK. Let's see how ephemeral CI can kill your developer productivity and what you can do about it. So my name is Louis. I work at Gradle. I want this talk to be really practical. You'll get the most out of it if you're already using Gradle and if you're suffering from some of the traps of ephemeral CI. But even if you use Maven or if you don't use ephemeral CI, I think there are interesting takeaways. Just a few things on the reason I'm around here. So I work on the Gradle Build Tool. It's JVM based. We're reaching almost 50 million downloads a month, which is a number I'll go back later on in the presentation. And yeah, as a build tool, it has an extensive plugin ecosystem. And while I work on open source, the reason I can be here and we can have a booth is because we have a product, and the product is effectively a data platform for build tools. Supports Gradle, Maven, SBT, Bazel. If you want to know more, please come to the booth. And one of the key pieces that we'll look at to illustrate some of the things I'm talking about today are build scans. There was actually a great session by Trisha G about build scans specifically. So that's it. That was the intro and some of the wordings around Gradle. So what do we want to do today? Well, I'd like to explain my problem statement. Why did I pick such a title? And why do I think it's an important conversation to have inside pretty much every single team building software out there? Then I want to explain to you what the profile of a Gradle build looks like. Because if you understand that, you will understand why I'm raising the challenges of ephemeral CI. And then after that, this is the tools in action. Let's be concrete and let's see what kind of actions you can take in order to improve the situation. So the basics of the problem statement is effectively looking at what makes Gradle a performant build tool and this trend that we see in the industry of using ephemeral environments. So why does build performance relate to developer productivity? Well, it's one of these aspects, right? It's not the only one, but it's the one I'm focusing on today. And one thing that we love to do at Gradle is play on word around the performance of a build. And if I ask you what is a fast build, it's quite a hard question to answer. Like, who says a 1 hour long build including test is fast? Yeah, pretty much no one nowadays, right? Half hour? Still not. 15 minutes? Still not. 5 minutes? I see a few hands, right? 30 seconds? Yeah, that's definitely fast, right? But even if it's 30 seconds, what happens if it can run in 5? That still is a huge benefit, right? I'm not saying you can run all our tests in 5 seconds, but in some cases, maybe. So if you take a look at the Gradle documentation, and we have a chapter around build tool performance, and it has a number of headers that you can follow. Turning on parallel execution, looking at caching, whether it's the configuration cache or just the build cache, increasing heap size, optimizing dependency resolution, doing specific optimisations for Android or pure Java builds. Like, all of these sections will come with a number of suggestions and avenues of investigation to improve performance. So we'll go in details about those, right? But then the second part of the problem statement, ephemeral environments. When you do things at scale, funny things start happening, right? If a machine breaks every 2 years and you have 700 machines, on average, you have a broken machine a day. And 700 machines in some organization might actually be a small number. If you don't count machines, but count builds, and you've got 1% of your builds failing, but you do 15,000 builds a week, that still is a lot of failed builds, even on a daily basis. And one of the ways that we cope with these failures, and especially the non-relevant failures, right? You change code, your tests fail. That's useful signal. It tells you something went wrong in the assumptions you made about the code you changed, or you changed something that the test assumed. But if your build fails because the agent disk is full, if your build fail because there were leftover processes that use the port that your tests use, if your build fail for all these many possible environmental conditions, this is a noise. You can't do anything about it. And it's a very frequent practice to say, oh, build fail, let me quick look at the results. Nah, it doesn't look related to what I did, just retry. And we'll see later on. But then back to the fast build, if you retry and it's 5 minutes, it's good. But if you retry and it's half an hour, it's not so good, because you already lost half an hour, potentially, and then you're losing another half hour to finally get your result. And so one thing that we see for quite some time nowadays is this usage of an environment that is both isolated and short-lived. So no initial state, and we shut down everything at the end. The no initial state means that we're trying to make sure that the second build or the third build or the fifth build is not impacted by artifacts left over by the previous builds. The short-lived is more about, hey, you know what? We just discovered that we're leaking connections in some database pool somewhere, but if you reboot the machine, they're gone. Yeah, obviously they're gone. And so the combination of those, I mean, they have justification, right? I talked about the scale of numbers. You no longer have state problems. You no longer need to clean up things. It's kind of magic. But it has a cost. And that's what I want to discuss today. It's the cost it has and why, in some cases, you may be interested in not throwing the baby with the bathwater, right? Like, there are useful things to keep around if they can improve that performance. So let's go back a bit more in details on those build tool performance characteristics according to the documentation. Parallel execution, the good news is, of course, you can do that. If you have modern hardware, it has parallelism capabilities, and if you can leverage them, you'll make everything faster. So, yep, that's a given. The Gradle daemon, so the whole point of Gradle daemon is to run on a hot JVM. Because once the JVM has the JIT kicking in, you get better performance out of the code, but that means you need to run multiple builds on the same daemon. And so in an ephemeral environment, if a single run is actually multiple Gradle execution, then yeah, you could leverage that. But if a single run on an agent is a single Gradle invocation, then you probably won't get the benefits of a hot daemon. Configuration cache. Well, configuration cache is a bit tricky. I'll explain a bit more later what the benefit is, but unfortunately, it's quite sensitive to the structure and the full path of your build because it has to capture all of the inputs. And so it's really hard to reuse if you do not have the exact same structure. It's something we want to do for later, but for the moment, that's not ready. And so effectively, this is most likely not something you'll be able to use in an ephemeral environment. Incremental build. Well, the whole point is that you change code once locally, you do more modification, you rerun a build, you want to limit the code that gets compiled and the tests that run. On an ephemeral environment, you obviously don't get that because the whole point is to not have that previous state. So definitely, we don't get that. The build cache, so when we talk about the build cache in Gradle, this is not just dependency cache, it's actually caching compilation outputs, test execution, all these kind of things. And there, the local build cache, most likely not, but the remote build cache, yes. You can have a remote build cache node, and nodes on ephemeral CI can actually go fetch entries there. So yeah, let's say you can benefit from the build cache. Having tailored workflows for specific operations, that always works, right? Hey, I need to run integration tests. The official distribution of the software includes the whole documentation, but we have a path that allows us to run with no documentation when we run integration tests on CI. That's obviously a way to win time, and whether you're ephemeral or not, you will win that time. And it's the same for the local developer workflows, right? You can optimize things based on the usage. So, yep, that works. Increasing heap size, we're back to the parallel execution. If you need lots of memory and you can give lots of memory to the machine, then you can do more stuff. Actually, it's even tighter coupled with the parallel execution, right? Because if you run tests in parallel, but a single test requires a gig of memory, and you want to run 10 of them, then you better have 10 gigs of memory. Otherwise, your parallelization will actually cause problem in your build. So there is a relationship there. But once again, this is tied to hardware sizing or virtual environment sizing. So yeah, it's a valid option. Optimizing configuration. I mean, if you optimize the configuration time of a build and you run less code every single time, it's going to be beneficial every single time. So this is, again, a practice that you should apply whether or not you have ephemeral CI. Dependency resolution. Well, the details of the chapter is mostly about how smart the Gradle dependency cache is. But that's a local on-disk cache. So if you do basic ephemeral CI without any kind of state restore, then you definitely don't have a dependency cache locally on the environment. And so, yep, that's going to be a hard sell by default. And then, of course, optimizing the specifics of projects, that's going to slightly depend on what exactly you're trying to optimize. But I mean, you can get the feeling of these question marks, like they are specific to some set of environments, which doesn't mean you shouldn't look into them, but just that you may have to effectively measure the benefits. And another way to look at the key performance elements of the Gradle Build Tool is to separate them by the kind of things we have. So we have caches. We mentioned the dependency cache, the task cache, the configuration cache. We have incrementality, everything that has to do with execution history, the ability to do incremental compilation, to only recompile things when an ABI changes and not when the implementation changes, all of that. And then we have parallelism, whether it's for tasks, for tests. And again, incrementality, not gonna work. I mean, the moment you destroy the project artifacts, which I think is the most critical state in ephemeral CI, right? That's the real state you don't want to keep around. It's the project artifacts. You won't get incrementality. Parallelism, throw beefier hardware. If you have a build that requires it, it's a quick win. It works. I mean, it's more expensive, so you still have to balance that, but it's a way to move forward. Caches, as we've said, it's a bit more complicated story. So now, how do these different performance characteristics participate in the execution of a Gradle build? And so what I want to do now is go a little bit more in details into the different phases of a Gradle build and see how they work together. I've got the comment on every single slide. The bars are not at scale. They're just an indication. Some of them, I've just made them bigger for fun. You have to measure, right? But it's an indication of the different phases. So at the highest level, if you're a Gradle user, you know about the configuration phase, which is where Gradle looks at what did the user request, and if I need to run those tasks, how many tasks, because there are task dependencies, do I need to actually schedule and execute in the right order so that the inputs to my later tasks are available. And while building the task graph, you could say, is a useful feature, the rest of the Gradle configuration is effectively, for your benefits, overhead. You don't care about Gradle having to run code. What you care about is having your compilation results and having your test results, or having your package application. That's what you care about. And that's what happens in the execution phase. But we need to remember that we're on the JVM. And so there is a bit at the start, which is the startup. I mean, JVMs have gotten pretty good at quick startup, but it still is something that matters. So if we focus on the startup, like I said, you run Gradle or Gradle W if you have the wrapper. That starts a JVM. If you're in a clean environment, which is what I'm going to assume, because then we can discuss all the different steps, the first thing the wrapper does is it downloads a distribution. A Gradle distribution, if you just take the binary one, is 100 meg right now, like 130. You can see that, right? If you do 15,000 builds a week and none of them have Gradle available, that's going to have a cost. Then we will start the daemon, which is the environment in which the build runs. While we still have an option to say no daemon, this option should be looked at more like a single daemon, so that you want the daemon to die at the end. Again, maybe in ephemeral CI you don't care because the whole environment is going to die, but we still use the daemon as a way to separate and make sure we have the right JVM arguments for your environment. But then there's something that not all people are aware of. When you run Gradle for the first time, we do generate a number of jars that we generate on disk, because if we provided them with the distribution, we would significantly increase the size of the distribution. And so we do some generation there. And that's a fixed cost. On that M1 Mac, we're talking about 8 seconds. 8 seconds for the latest Gradle version, because in the past, we were actually generating more jars, and it was more like 12 seconds. So if we go back to that 30 seconds was a nice timing for a build, you can imagine if every single ephemeral CI invocation adds 12 seconds to that number. Like, it's almost 50% more. Then, during the configuration phase, we have to do plugin dependency resolution. Like, the way you extend the capabilities of a Gradle build is by declaring plugins. Those are effectively binary jars that you download from a repository. We have to resolve that graph of dependencies. Then we need to compile the build logic. This is why also we download the dependencies first, right? These dependencies are part of the compilation class path for the build logic. And then finally, we can create that model of your build and their projects and build a task graph of everything that needs to be executed. And once we're done with that, we're good to go. Like I said, task graph building, we could consider that it's a value add of Gradle, because it means you do not have to invoke all the single tasks to make sure that your test task has all its correct dependencies. Gradle does that for you. But pretty much everything else we've seen so far could be considered tooling overhead. And while we try to keep the tooling overhead to the minimum, I guess you got the point of my presentation, if you play in an ephemeral environment, you're actually reintroducing a number of those overheads, whether you like it or not. And then finally, the execution phase. We again do dependency resolution. It's pretty much the same process as for the plugins, except that we now talk about the dependencies of your production code and your test code, which are needed for both compiling and running those tests, and compiling the production code, obviously. Then my inputs fingerprinting, task execution, it's a way for me to say task execution is really what you want. Hey, run the compiler. Hey, run check style. Hey, run Jacoco. Hey, create a reports of something. But because Gradle tries to be smart about what needs to run and what doesn't need to run, we will compute, like, effectively identifiers for all of these tasks to verify whether the current state we have on disk is correct or not. Technically, it's not a single block followed by a single block of execution. You have to imagine it's like tons of small slices where fingerprint, execute task, because the fingerprinting obviously depends on the task, but also can depend on the results of the previous task. But it still gives you an idea that stuff happens. This is probably the biggest place where the folks responsible for that whole system would scream at me because I made inputs fingerprinting way too large. It should be much smaller. But you never know. So, now that we understand that, and that we remember the premises of the ephemeral CI conversation, what can you do? Well, the good news is, actually, you can do a lot. But the first thing you need to do is, this is performance. If you lift a finger to feel where the air is coming from, and then do changes, you might actually do things that are harming the project and making it even slower. You need to measure, then do a change, then measure again, then compare, and then decide, was it worth it? None of the stuff we do needs to be taken for granted. We have tons of optimizations in Gradle, but we get our stuff wrong. We released 8.7 a couple weeks back. One of the features that we announced was that we would cache the compilation results of Groovy scripts. It wasn't the case before. The net impact on some large-scale users of Gradle is that their clean build went from 2 minutes to 9. Because they have very simple build scripts, the Groovy compiler inside a hot Gradle daemon is actually pretty efficient. But if you have thousands of those build scripts and you try to talk to a remote build cache for every single one of them, what you start accumulating is the latency between the build and the cache. And I mean, for us, the benefits were there. But at scale, depending on your setup, yep, maybe not that way. So always measure, change, measure. So let's start by optimizing the Gradle startup. First of all, don't use the old distribution. It contains the documentation, the sources. I mean, while you want that information in your IDE, nowadays, if the Gradle wrapper uses the binary distribution, which is the smaller one, the IDE will download the documentation like the Javadoc and things like that. So always use the binary one. Bake it in. Whether you've got an AMI, an AWS AMI, or a Docker file or something like that, there are chances that you can standardize on a few Gradle versions across the organization and make sure that you upgrade them with a similar pace. When you do that, then bake them in, like make them part of the image. Yes, the image will be slightly larger, but it's 100 megs that you don't have to download when you start a build. Or use a mirror which is closer to your ephemeral agents. Or even, you could just, after a run, grab the content of the Gradle user home, wrapper dists, and copy it to the next agent. You could tell me, yeah, but like the file copy might break builds because there might be a write error. Yeah, sure, but the download could exactly be the same. Will you win or will you lose something? I mean, again, you'll have to measure, but it's very likely that it's going to be close. The second step is we need to prime the distribution. Run it once. Run Gradle help on an empty folder. You will see Gradle starting a daemon, generating jars, and then saying, hey, there is no project here. Here is what you can do, and here is the standard help message. And then after that, you can run builds. And again, that step is something you can do when baking that image, when creating that Docker file. Or, once again, you could decide to just save and restore the files that you'll find inside the Gradle user home. So yeah, that's what the JUH stands for. Caches version being the Gradle version, and then generated Gradle jars. If you copy those files around, and they're not that big, or if you make sure that they're part, again, of your base image, that's it. Gradle will not need to do it. It will find the files and happily run with them. So I said I would go back to the downloads over time. 49 million is a pretty good number, like for an open source project. But it's a vanity number, right? I'm not sure it's fully visible, but like effectively a year ago, we were at 30 million. So we've done almost plus 20 in a year. This is crazy. And these are not humans, right, downloading Gradle. These are effectively GitHub actions, GitLab actions, and other kind of ephemeral environments just downloading tons and tons and tons. Like we have large-scale users that do 100,000 of build a week, and they count for one download. Because they'll download it once, have it locally in one of their servers, and we will never hear about them anymore. So these 50 millions are like not even representative of the exact population of Gradle users. Let's continue. So the second step, if you remember, was the configuration phase. So first of all, we can use the dependency cache. The dependency cache, we've got different ways. If you have physical machines that run multiple Docker containers, we have a read-only feature. So you could have, like you could at some point extract a dependency cache from one of your largest builds or from one of the builds that exercise the most code and copy that over and then mount that as an extra resource in Docker containers, for example, so that all the builds can benefit from that cache. What they'll do is, if it's properly configured, they will look there first, and if the file is there, use it, and if it's not, then they will start populating their own cache, because we don't want like multiple builds trying to write to the same cache. That's one of the issues you can find in non-ephemeral environments. And when it happens, it's really weird. Like you get a corrupt entries in the Maven local cache or in the Gradle dependency cache, and you're wondering what happened exactly. Or again, save and restore. Gradle user home caches modules too. That's pretty much all of your dependencies or all of the dependencies of the build cached. Then we've got the script compilation cache. I mean, I guess I kind of sold the problem there. But the remote build cache is one solution, maybe, right? In the case of Groovy script compilation, if you have lots of simple Groovy scripts, maybe not. Or again, save and restore. We have caches, again, Gradle version, Kotlin DSL, that's for the Kotlin scripts. Caches version script, that's for the Groovy scripts. You can see the difference, right? When the cache for Groovy was made, Kotlin was not yet on the board, so it's just called scripts. Kotlin appeared, we have an explicit name there. Jars 9 is actually, and especially in the latest versions of Gradle, we run with instrumentation of your build scripts in order to make the configuration cache work. And so if you were able to reuse configuration cache, that would be one step where you would effectively cache all of this phase completely. It's possible on CI, but it's tricky. So yeah, that's not as easy as it sounds. We're working on that for the future. And then finally, on the execution side, I mean, dependency cache, task execution cache, again, remote build cache, or you can save and restore things. Android mostly, you can also restore these transforms. So that's, again, one of the features Gradle uses to use like an Android application archive and then explode it in these different components and run things on the separated components. If you use toolchains, you can also save and restore the JDKs. We released with Gradle 8 a provisioning system that uses the Fuji Discovery API to provision JDKs. And that API started having stability issues. Like it would go down. And so we were in touch with them, and at some point they contacted us and they said, you know what, folks, it's actually you. It's Gradle builds hammering us because like we now have a usage of the API that's crazy. Like they don't offer the downloads, but just the requests for saying, hey, I want a Java 11 with that kind of characteristics, which URL should I use? That was enough to bring them down a couple times. So once again, it's an illustration of the waste that happens in that context because it means all of those builds will keep downloading JDKs. So what does it mean in practice? And that's where I need the glasses. So I have a plugin, and I used a couple runs of GitHub Actions to illustrate things. So that's a very simple GitHub action. I don't even use the Gradle GitHub action. I just did a basic invocation once I've set up, like check out the code and install a Java version. Then what we can see is that like my build takes 2 minutes and 14 seconds. I've got a 6 seconds initialization phase, right? That's effectively generating jars. 42 seconds configuration, and then 1.5 minutes of execution. If I look in the log, I will see that the build execution starts with the loading, reminding me of all the highlights. Yeah, of course, that's the thing we don't show you the second time you run a build, but it's always a clean environment. And then all the stuff happens. So then I moved on to the GitHub action for Gradle. And what we can see is that, so I publish build scan, so I can see like the build scan immediately from the action result instead of having to dig through the log. But effectively, we're again in a similar duration, right? 2 minutes 40 seconds compared to 2 minutes 30. Yeah, so a bit the same. But if I look at my scan, like it's very, very similar. 4 seconds instead of 6, 44 seconds, 1 minute 25. What did I win? Well, on that execution, not much, right? Because that execution didn't have anything in the cache. Now, of course, I'm rerunning the same commit, so this is not fully relevant, but the whole point is that when I rerun my build, I get a result in 30 seconds. That's 5 times faster. I mean, whatever the long time of execution you have, if you can divide it by 5, it's pretty good. It's a very small project, so that would not scale to you doing changes to the project. But if you have got a larger project where you do changes only in a subset of the sub-projects of your build, it can have that kind of impact. And what we can see is that effectively, my total build time is actually 8 seconds. So the overhead of preparing everything is now completely different. But yeah, I've got 2 seconds of initialization. I no longer generate anything. 5 seconds of configuration. And then, of course, I've got a build which is fully up to date, so that's half a second. Like I said, you will not get the same result when you do meaningful changes, but still it shows you what's the extreme. And once you get an extreme, then you can start looking at how it impacts like developers. And so in terms of conclusion, what we can see is that if we're smart and we look at the different phases of a Gradle build, even if you use ephemeral CI, there are a number of things that you can actually cut off by being smart in restoring state, which again is not the problematic state of your project's artifact, but actually state related to the environment. That's what I had for you. Time's up. I'll be at the booth. I'll be outside. I'm happy to take questions after. Thank you.